Hello, everybody. Welcome. And thank you very much for making your comments that there is no sound. I also said it looks like it's somebody's birthday today, at least according to the chat. So happy birthday to you. Now, if this is the first time any of you have come to the Ask Math Anything, you're in for a surprise. And so am I. And that's because all of this is driven by whatever you guys ask. This is an unusual math class in that sense, because in this math class, not only does everyone here learn, so do I. So, if you have been here before, I'd first like to welcome you back. And as you know, the rules are basically, please ask questions that might make sense to people who are studying algebra or geometry. Actually, I should be careful. I shouldn't say ask questions that make sense to people who are studying algebra and geometry. I mean ask questions for which my answer might make sense to people who are studying algebra and geometry. And what I'll try to do is I'll try to find a way to answer even questions that seem a little bit strange to people who are studying these subjects. Okay, I think we should go ahead and get started. So what kind of questions should we talk about today? Okay, here's a question to start off the whole day. This question is, somebody asked, first off, why is it Friday? Maybe the date is not quite right on this particular YouTube picture, but the good news is it doesn't matter, because you're obviously here anyway. Unfortunately, the people that we need to tell that the date was wrong are not in this live stream. But let's start with a question to warm up. The question is, how many integers n from 1 to 100? So the question is, how many integers n from 1 to 100 have the property that n to the power n is a square? Oh, this is easy. Obviously, all you have to do is you just have to say it's a square if you happen to be raised to an even power, right? So it's just the same as how many even numbers are there from 1 to 100. How many of you agree with me? Well, sort of. That's not quite the answer. That's not quite the answer. This is a trick question, right? So there's one way that this can be a square. One way is that you have n to the power even. That would work, right? And so if I happen to have n to the power an even number, we're good. And so what this gives you is it gives you 50 that work. All the even numbers. But if you took 1 to the power 1, that's also a square. And 9 to the power 9 is also a square. So there's the other way, which is if you have already gotten a square and you happen to raise it to an odd power. Now I'm saying it's other way. Since I said other way, I need to have that this is not already counted in those 50. Okay? So if I have a square to odd, I guess that's just asking how many odd squares are there? How many odd squares? And for that, we just say, well, we're going from 1 to 100, right? So you have 1 squared, 3 squared, 5 squared, 7 squared, and 9 squared, and that's already 81. Now, 100 is 10 squared, so you wouldn't go to 11 squared. So here, you have 5 that work. And so I think that the answer to this question is 50 plus 5, or 55. Do people agree with me? Seems good, seems good. Okay, so I think this is good, and in that case, we have answered this question. It's a nice one to start with, because as you can see, it's a bit of a trick question. At the beginning, people would say, oh yeah, it's just 50, we're done. But you have to be careful of the other ones. Okay, next question. Anna, how? I am even. Yes, even and odd is the heart of this question. More questions. Whoa. Can I do this problem? I'm not sure if I can do this problem. It could be too hard for me. When I say too hard for me, I mean too hard to do for real on the live stream. It's also fairly difficult compared to Yeah, compared to a lot of the questions that people ask. But I'm a little bit curious. So you're telling me that if I look at a sequence, 1, 31, 331, 3331, and like keep on going, you want to show prove there are infinitely many composite numbers there. Now this could be too hard, and the reason I say this is too hard is because a lot of number theory problems look really innocent, but it turns out that they are actually quite complicated. And so what I'll do for this one is I'll just play a little bit. I'll just tell you what I would think if I was trying to answer it right now. Yes, this looks very hard, and we might not be able to do it. But I'll tell you the only thing that I think of. When I see that there are all these threes, it looks to me like there's a formula for the nth term. And so I'd be a little bit curious if I can at least write down the formula for the nth term, and then maybe we'll give up at that point. And something else I was looking at is I was like, does this follow any one of these like big theorems? There's some big theorems that say if you have an arithmetic progression of infinite length, then there are always, oh, actually that one says there are always prime numbers there. But here we need to show there are infinitely many composite numbers. By the way, that's fairly likely. You know what? Actually, to prove there are infinitely many composite numbers, now that sounds more doable because composite numbers are more likely anyway than prime numbers. I mean, come on. If it was only finitely many composite numbers, then you're telling me that we have a magical way of making a whole bunch of prime numbers? That would be pretty impressive. Actually, it would be pretty impressive if this was false, because then you would have a magical way to make lots and lots and lots of prime numbers. Okay, but now what I'll say is, can anyone think of a good formula you can make? The reason I pulled this one out is because all these threes, like 3, 3, 3, 3, 3, 1, it looks like it might be related to something I could write a formula for. Because you see, if I wanted to say, look, I've got 3, 3, 3, 3, I can tell you a formula for 3, 3, 3, 3. I see that Vera 1 is thinking about maybe a geometric progression. I was going to do something easier. I was just going to say 3, 3, 3, 3 is 9, 9, 9, 9 divided by 3. But 9999 I can write with a 4, right? The point is this is a 4-digit number. I'd like a formula that has a 4 in it. So it seems like I could write that as 10 to the power, I don't need parentheses, as 10 to the power 4 minus 1 over 3. So now I happen to have a formula for this 3333. And that has a 4 in it, which makes sense because I have 4 digits. So now I might want to say, can I go and make a formula for this number, 3331? Yes, I can. 3331 is then equal to 10 to the power 4 minus 1 all over 3, and then minus a 2. So by the way, now I have a formula for the nth term. The nth term is just going to be 10 to the power n minus 1 over 3 minus 2. Okay, so let's see. Nth term is equal to 10 to the power n minus 1 over 3 minus 2. But who in the world writes minus 1 over 3 minus 2? Let's just go and put them all over a common denominator. I'm curious if this will help. So this is equal to something divided by 3, 10 to the power n minus how much? Oh, I made the fraction too big. I don't need such a long line. It looks like it's what, 7? Looks like that's what I have. 10 to the power n minus 7 over 3. Okay, so now what I need to do is I need to know, could it be, is there any way to show that this thing somehow is composite infinitely often? For me to show it's composite infinitely often, what do I need to do? What could I do? I'm thinking. It'd be great if 10 to the power n was a multiple of 7, but that's not going to happen, right? 10 to the power n won't be a multiple of 7. On the other hand, I'm trying to think about remainders. First of all, it's nice that somehow when I divide by 3, there's always this remainder. I wonder if I can show... No, I was going to say I wonder if I can show it's always a multiple of 3. No. I wonder if I can say something about... Yeah, okay, now I have an idea. The idea I have is, I wonder if I can show that infinitely often it's a multiple of 11. Would that be possible? 11 is unlikely. 11 won't work. What I'm trying to do is I'm trying to use these tricks of modulo something. Again, we're going maybe a little bit more difficult in algebra or geometry, but I think we might actually be able to hit this one. The thing I'm thinking about here is I'm trying to say, look, if I have 10 to the power n minus 7, if I think about what is the remainder of 10 to the power n when I divide by something like 13, I wonder if I'll be lucky, and at some point, 10 to the power n is a multiple of 13. Ooh, I've got it. Okay, so what I'm going to say is yes, actually, infinitely often, I bet we can get that infinitely often is a multiple of 31. Let's do that. And here's why I'm thinking of 31. The reason I'm thinking of 31 is I know that at one point it's a multiple of 31, and if at one point it's a multiple of 31, then I bet I can get it to be a multiple of 31 again. Let me show you why. And this is the inspiration. I see a 31 here. I think we can actually solve this. Okay, so now I have a claim. I can get 10 to the power n minus 7 over 3 to be a multiple of 31. I don't know if this claim is true yet, but I'm pretty sure it is. Infinitely often. If I can do that, then certainly it's going to have infinitely many composite numbers. And here's how I think I can do that. Because you see, in order to show that this is a multiple of 31 infinitely often, I just need the top to be a multiple of 31 infinitely often. Because dividing by 3 can't get rid of my 31. There's something magical about this sequence. The sequence is always a whole number. And I know it's a whole number because I used the whole numbers to make this formula. Okay? So it's enough to show (10 to the power n minus 7 is a multiple of 31 infinitely often. Okay? And that's all I'll need. As long as I know that that's a multiple of 31 infinitely often, if I divide it by 3, since I know for sure it's going to be an integer, that won't get rid of my 31. Now here's how I know that this will work. It's because I already know, like 10 to the power 2 works, because we saw a 31 there. We saw n equals 2 gave a multiple of 31. And you can even see, if n equals 2, that was 100 minus 7, which was 93. And you also see we were going to divide by 3 at the end, but you'll still get your 31. Now there's something else that's very powerful that you can use, because I'm going to talk about what happens when I look at the remainder, when I multiply a number by blah, 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 multiplying it by stuff, modulo 31. And I guess this one is for any one of you who actually took my number theory course. My number theory course, I believe, has something that might be related to this. But what is going to happen is that there's a interesting theorem. There's a very interesting theorem. It's actually called Euler's theorem. Oh, I don't need Euler's theorem. I can use Fermat's little theorem. And Fermat's little theorem says this. If I take 10 and I raise it to the power 30, do you know what the remainder of that is when I divide by 31? Can somebody with Wolfram Alpha or a big calculator, could you help me out? Can you calculate 10 to the power 30 and then divide it by 31? Do you know what the remainder is? 1. You did it so fast? How'd you do it so fast? Is there anyone who has a way to just type this in? 1 or 0, cannot remember. But the good thing, I'll tell you, it cannot be 0. Because in order for it to be 0, you have to be a multiple of 31, which you don't get by multiplying 2s and 5s. But is there anyone with a big calculator? Your PC is totally a big calculator. It's just you go to Wolfram Alpha or something. Oh yes, X Her got this big crazy number, but you want to have it in Wolfram Alpha so you can really divide and see a remainder. All these people are saying the remainder is 1. Okay? All these have a remainder of 1. Why do I care? The reason I care is And by the way, that's Fermat's little theorem. Fermat's little theorem says that if you have a prime number here, if this 31 is a prime number, and if the 10 has no common factors with the prime number, then the number to the prime minus 1 modulo the prime is 1. Okay? It's a cool fact. And you can, 3R2. Really? Are you sure? But I see that somebody has a nice answer. It's something remainder 1. Okay? But it's a remainder of 1. So now, if I've got this remainder of 1, why do I care? The reason I care is, so, if I write 10 to the power 30, that's equal to 31 times something. But the something is a whole number. And then plus 1. All right. Now, why is that exciting? The reason that's exciting is because I have a feeling that if I took n equals 32, it could be interesting. For n equals 2, I got a multiple of 31. I'm curious. I'm going to do a magic trick, and it might fail, but let's try. Can anyone tell me what the answer is for n equals 32? For n equals 32, what I mean is 10 to the power 32 minus 7. Right? I'm doing 10 to the power 32 minus 7. While the police is going by, let me just write it here. Now, if I did 10 to the power 32 minus 7, can anyone tell me what is the prime factorization? Or not prime factorization. Can anyone tell me what happens when you divide this by 31? What's the remainder? Ooh. 0. Did you guys actually do it? Or did you just use math and be like, math says it should be 0? If you actually type this into a big calculator, no, not 7 divided by 31, I'm sorry. Oh my gosh, I should be careful of order of operations, good gracious. Okay, yeah, 10 to the power 32, then minus 7, and then divide by 31. Yes, apparently the police are after me, I don't know, fortunately they haven't knocked on the door yet. But I'm going back to this thing, right? So back to this thing, 10 to the power 32 minus 7, and then divide by 31, remainder 0. Hey, look at that, I got another one with remainder 0. Now, does anyone know how I guessed 32? Why did I guess 32? How did I use what I saw here to guess that 32 would be pretty good? 30 plus 2. It's because I knew that 10 squared minus 7 would work. And I knew that 10 to the power 30, if I divide by 31, has a remainder of 1. And so let's look at this. I'll put this together. This is actually really cool. What did we have? Let's combine some facts that we knew. We combined this. We knew that 10 squared minus, not 1, minus 7 is a multiple of 31. We knew that. We also knew that 10 to the power 30 was equal to 31 times something and then plus 1. And from these two observations, what I decided to do is I said, all right, let's do 10 to the power 32. Why do I care about 10 to the power 32? It's because that's equal to 10 squared times 10 to the power 30 and then minus 7. Okay? But why this is good is because now let's use what was the 10 to the power 30. 10 to the power 30 was 31 times blah 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 plus 1. And then minus 7. Aha. Now, if what I care about is what is a multiple of 31 and what is not, then this is equal to 31 times even more blah, 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 because that's the 10 squared times 31 times blah, blah, blah. So this lump, this loopy lump is 10 squared times this squiggly lump. That's what happened here. These two lumps, this lump combined with a 10 squared. Okay? And it became like a loopy lump. But then I still have more stuff. I have plus 10 squared minus 7. Okay? But this is good. The lumps return, you guys say, right? Because now I have 31 times some lump plus, a multiple of 31, right? I know that 10 squared minus 7 is a multiple of 31. So there's a multiple of 31 times a multiple of 31. So the answer is, okay, since you guys like lumps so much, it's 31 times another lump. And that other lump is just combining this lump and whatever 31 times 3 from here. Okay? So what I've just shown you is that the fact that the 10 squared minus 7 was a multiple of 31 lets me know that 10 to the power, and also that 10 to the power 30 is a multiple of 31 plus 1. That's how I knew to combine the 10 squared and the 10 to the power 30 like this, because then if I blow up the 10 to the 30, I get some lumps plus a 1. And that 1 joins with the 10 squared to just give me back the 10 squared again, because this is back to my favorite 10 squared minus 7, which is a multiple of 31. All right, so what I've just showed you is that somehow because 10 squared was a multiple of 31, and 10 to the power 30 somehow didn't change my multiple of my remainder when I divide by 31. That's what really happened. Then I did 10 squared times 10 to the 30, and boom, I got another one. Hey, does anyone want to tell me another one that works? N equals 2 is a multiple of 31. N equals 32 is a multiple of 31. What's another one? Can someone tell me another one that should work also? What's another number? 10 to the power 62 minus 7. Let's do it. What is it? This will just show us that math works. 10 to the power 62 minus 7. If I divide that, who's got the big calculator? Divide that by 31. Don't tell me what, I was going to say don't tell me the remainder, tell me the quotient. But I don't want to know the quotient. The quotient will be too long. Remainder. What is it, everyone? You guys happen to have some kind of big calculators here. I don't know. Who's got their finger on the Wolfram Alpha? 10 to the power 62 minus 7, all divided by 31. C++, you say. 10 to the power 62. 10 to the power 62 minus 7, then divide by 31. Yes, 0 popped up. Remainder 0. And it worked. So actually, I thought this question might be too hard, but it turns out it wasn't too hard. It turns out that we were able to go and look at this and find out that actually, yes, there are infinitely many composite numbers. In fact, there are infinitely many numbers that are multiples of 31. And why did I choose to go and poke on 31? The reason I chose to poke on 31 is I knew that 31 already appeared. So I knew that actually it would be possible. I knew it would be possible to get a remainder, to get something divisible by 31, because I see it there. And if it was possible to do it once, then I'm sure I could do it more times, because when I looked at the formula, I said this formula never divides by 31. By the way, I'm now giving you a hint. If any day you ever qualify for the USA Junior Math Olympiad or the USA Math Olympiad, this is kind of how to think about these kinds of questions, right? And so it's like somehow I'm never going to have to divide by the 31, and therefore the fact that the 31 lives there means that this numerator, it's possible for the numerator to give a multiple of 31. And the way that number theory works with these kinds of expressions, if you got it once, you often get it infinitely often. And so that's what we did. All right, so that was this question, far too difficult for the usual level. If you got scared away, please come back. I'm not sure that makes logical sense. Hopefully you're not actually scared away. We're going to go and do some things that are a little bit more approachable. But maybe one thing, no matter what you're learning in math, I hope you found it somewhat interesting that you can write down these numbers as these kinds of expressions. And if you write these kinds of expressions, then you can often go and stare at them and then just use some divisibility or some, what happens with this taking different powers of a number and looking at remainders. Next question. No, it is an IMO problem. This is an IMO problem? I can't believe it. Wait, are you serious? This was actually an IMO problem? It strikes me as a little bit too easy. But I actually don't know who asked this question. But whoever asked this question, I'm actually a little bit curious where you got this from. Jeffrey Lee says, 3331 is not divisible by 31. You are right. And I didn't say that every number is divisible by 31. The problem only needed us to get that there are infinitely many times that it's composite. So if I just get infinitely many times that it's divisible by 31, I'm done. And by the way, if you're curious about understanding this a bit more, actually the fact that 331 is not divisible by 31 shows that you can probably also make it infinitely often divisible by 331. I actually don't know if 331 is prime, but it looks like it could be. I'm not sure it is, but it could be. Okay? I still don't know exactly where this problem came from, but if somebody actually knows where this came from, please do let us know, let the moderators know. If this is actually a legit problem from some contest, please do let me know what contest it was from, what problem number it was from. Moderators will put it into my chat thing, and then I'll be able to make some comment. Okay. All right, more questions. Looks like we're talking about prime numbers today. I'll take another prime number question. I'm a little curious what the answer to this one is. And this one will be a lot easier, I promise, a lot easier. So this question is, wait, Rithik Gumpu says this is an IMO problem. No, we're not going to do more IMO problems here. This is supposed to be something which is understandable to everybody. Okay. And as you can see, I'm kind of one of these people who's susceptible to saying, ooh, that looks interesting, let's go and play with it. But I don't want to lead everyone astray with something that would be too hard. Instead, here's another one. Manasa K. What is the smallest prime? Oh, back to primes. But the smallest prime whose digits sum to 19. So this looks kind of interesting. 199. Oh, is that it? Maybe we're done. Let's see. So the reason I said this looks reasonable is because I was pretty sure that some 3-digit number will have primeness and digits sum up to 19. And if that's the case, we'd be in good shape and we'd be done. So first of all, you can't do 2 digits. 2 digits is at most 2 digits is like 99. So now the first thing you try with a 3-digit number, in fact, the smallest 3-digit number whose digits sum to 19 is 199. That's the smallest 3-digit number that I could use at all. All right, let's test for primeness. Is it divisible by 3? Sorry, is it divisible by 2? No, it's odd. Is it divisible by 3? No, because if I add up the digits, it's not divisible by 3. That's one of these divisibility by 3 tricks. Is it divisible by 5? Oh no, the last digit gives it away. How about 7? I have to check. 7 times 2 is 14. 59, no way. I'm not even going to bother finishing. Not divisible by 7. 11. Is it divisible by 11? The 11 trick is you kind of add the 1 and the 9 and you subtract that 9 in the middle, and so it's 1, and that's not a multiple of 11, so no. If you're curious about all these divisibility tricks, the best way to learn that stuff is in a number theory class or a number theory book. And there are these quite standard tricks that have quite nice proofs. How about 13? I have to actually divide that. 199 divided by 13. Actually, I don't have to divide that. The reason I don't have to divide that is only because I happen to know that 13 squared is 169. So here's how I'm going to be lazy. Lazy approach. 13 squared is 169. I just happen to know that. And the more of these problems you do, the more often you see that. And if 13 is the smallest prime factor, because none of the other things worked, right? 2 didn't work, 3 didn't work, 5 didn't work, 7 didn't work, 9's not prime, 11 didn't work, 13 is the first one I'd try. Well, the next thing you could use, remember, if 13 is the smallest prime number that divides into 199, then the prime factorization of 199 would be 13 times bigger primes, right? So what I'm going to say is too lazy. Too lazy, right? So what I'm asking is 199 equal to 13 times bigger primes? I mean, first I checked if it's 13 times 13. It's not 13 times 13 because 13 times 13 is 169, so it didn't match. And what are the only bigger primes? The next thing would be, well, the bigger primes are at least 17, right? If I had 17, if I had 13 times 17, 17 is the smallest bigger prime. And there's a nice way to multiply 13 times 17. Does anyone know the most efficient way to multiply 13 times 17? 13 times 17 is sort of like 15 times 15, right? That's 15 minus 2 times 15 plus 2. And that's a difference of squares. That's equal to 15 squared minus 2 squared. If you just go expand this out, 15 times 15 plus 15 times 2, minus 15 times 2. That cancels. And then minus 2 times 2. So that's equal to 15 squared minus 2 squared, which is 225 minus 4, or 221. And so I know that if I took 13 times 17, it's already bigger than 199. So this is the lazy way of seeing that 199 is prime. Of course, this might have looked like it takes forever for me to write this down, but if you do this in your head, let me recap. Like, here's what I did. All I did is I said, I'm too lazy to divide by 13. That's just hard. If I want to divide by 13, I just went and checked. 13 squared, 169, no match. What's the next biggest prime? 13 times 17. Ooh, 13 times 17, that's going to be 15 squared minus 4. That's going to be 221. Too big. So no more. There's no way it could be even bigger primes. Done. And I was able to be lazy. Didn't have to do this. Did that sort of make sense? Too fast. Okay, let me slow it down a little bit. So this is actually quite important because it's a great shortcut. Okay? So if I'm doing prime factorization, I went and tried to divide by all the primes where I start small and I get bigger and bigger. So I went and found out that 199, it doesn't have any prime factor, which is 2. It doesn't have any 3. Doesn't have any 5. Why didn't I check 4? I didn't check 4 because 4 is not a prime factor. If I prime factorize, I try to divide by all of these prime numbers. So I try and I try and I try, and I see it's not even got an 11. And finally, I'm now curious about 13. Is 199 divided by 13? Does it have a remainder of 0? The easy way, or the brute force way to do it, is to actually go and divide. But that's too lazy. There's a question. How did you get 199? The way we got 199 is because we said, if I want digits to add up to 19, and I use 2-digit number, the biggest I can get is 99. The sum is 18. So I need to have 3 digits no matter what. Now, if I need to have 3 digits no matter what, I may as well choose the smallest 3-digit number, which is a 199. That's the smallest 3-digit number, which has the digits adding up to 19. And then we hope for the best. We hope that this actually is prime. And what we're doing now is we're just checking whether it's prime. And the way that we check whether it's prime, I'm now checking about the 13. So I say, let's divide it, but I got too lazy. So then what I said is that, I already tried dividing 199 by other primes, all the way up to 13. And I didn't find any that worked. So if 199 is not prime, the only possibility is that 199 is 13 times stuff. But the stuff has to be bigger than 13. It has to be made of bigger primes than 13 to be specific. Right? Because I tried dividing by all the smaller primes, none of them worked. So my prime factorization would be 13 times stuff that's bigger. When I say bigger, I mean bigger could also include 13 again. So then what I did is I said, would 13 times 13 work? Unfortunately, that doesn't work. 13 times 13 doesn't match. 169 doesn't match 199. And so this is not going to be 13 times stuff. Next, what I said is, what if I try a bigger prime? The next bigger prime is 17. So if the 13 didn't work, it would be 13 times 17, or 13 times even more. And if that's the case, well, let's try 13 times 17. 13 times 17, there's a mental math trick that is 15 minus 2 times 15 plus 2, which if you multiply that out, it actually makes 15 squared minus 2 squared. And 15 squared is 225. I'm just showing how it's useful to have a few squares in your head. And 225 minus 2 squared is 221. So now I know that if I did 13 times a bigger prime where the prime was already 17 or higher, it's too big, 221. It's already bigger than 199. So if I try even bigger primes like 19, I'll get even bigger numbers, and it just won't work. So that was the discussion of, why is this a lazy person's approach? Lazy person's approach doesn't actually have to do this division at all. Effectively, what I'm showing you is I prefer to multiply. I don't really like dividing. When you divide, you have to do all this like guessing and subtracting and guessing again, and 2-digit divisions are no fun, but multiplications are sometimes not bad. Okay, let's take some more questions. What else do we have today? Oh, this is interesting. Cool Kid asked, when 9 factorial is expressed as an integer in base 9, the result ends in m zeros, and the last non-zero digit immediately preceding the m zeros is n. What is the value of the ordered pair mn? So that question, I believe, is on one of our live streams. That looks very familiar. I wonder if that one was a question in math counts. Is that right? I have a feeling that, yeah, that was in math counts. So all I'm going to tell you is, if you want to see the solution to that question, just go back and check this particular YouTube channel's saved video from maybe last month, middle of last month, when we talked about the math counts solutions for this year's chapter math counts sprint round. And it happens to be in there. So just go there and you'll see the full explanation. Okay, more questions. The Real Paperboy has asked us to do a question which is a puzzle. Let's try this puzzle. No number theory on this one, don't worry. Let's try. So we have these numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. And what we're supposed to do is we're supposed to make them all become 100. Okay? So we need to have some kind of an equation. This equals 100. And what you're allowed to do is you're allowed to use addition, subtraction, multiplication, and division. You can do it more than once. Possibly more than once. But the numbers must stay in order. So here's the question. Is it possible? Did we do this one? I don't remember this one from the numbers staying in order. So maybe we did this one, maybe we didn't. We've done a lot of questions like this. Can you combine? I'm not sure. The question didn't say that we could put it together. And you're right, we did similar problems. But every single one of these problems is like a little bit different, right? So I just put this here because all these details make a difference. If you are allowed to do like little changes in your problem, sometimes the problem has a different answer. And no combining digits. No combining digits. No combining digits. Okay? Yeah, just smush the 5 and 6 together, but I think that we're not supposed to smush them together. Can we ram it with a low mobile? This is pretty good. You guys are great. So what could we do here? So if I wanted to think about this, I would say I am a greedy person. When I say I'm a greedy person, I would like to, get close to 100 first. Is that a good idea? Yeah, because like 9 times 8, that seems pretty good. Let's try that. 9 times 8 is 72. We need to get close to 100. So the easiest way to get close to 100 is, boom, we got a 72. So if we got a 72, how much more do we need? 100 minus 72 is 28. When I subtract like these kinds of numbers, I just know that I take the 9 minus the 7 is the 2, and the 10 minus 2 is the 8, because I know I'll be carrying. So that's why I did the subtraction where I went from left to right. But so I need to get 28. Oh my gosh! Hey, that's why somebody said 1 plus 2 plus 3 plus 4 up to 7 is 28. Because it is. Because 1 up to 7, if I add them all together, it is how many of them, which is 7, times the average. And the average is 4. 7 times 4 is 28. Hey, it works. You guys just saved us a ton of time. You add them. And this is also consistent with the approach that I wanted to use. The approach I wanted to use was to say, if I want to solve this problem, let me first get close to 100. Was that luck? Well, it was, I think, the luck that somebody asked us a question that was quite reasonable. But the way that I thought of this also was, I want to get close to 100. The easiest way to get close to 100 is 8 times 9, 72. Once you got 72, then you can see I need 28 more, and 28 is what's called a triangular number. It's a number you get from adding 1 plus 2 plus whatever in order. And so at that point, it actually just works out. It's 28 plus 72. Nice! I think this is pretty beautiful. This is pretty good. Okay. Oh, Minko said, I did this problem before in a math contest, I think. Right. So these are kind of nice. I mean, I don't think we did this one in our live stream before, but I like it. Okay. What more could we do? Hmm. I see that a lot of people are asking questions about Bob the cat and catching mice and jumping. And I'll even tell you one of them that strikes my interest that I'm looking at right now is that it's from Michael's son. Bob the cat is eating mice. He has 2/3 chance of catching a mouse when he pounces. How many times does he have to pounce to get a greater than half chance of catching 10 mice? Now, there's a reason I didn't write this on the board. It's because these kinds of questions, that like that one you've just asked, it's not the kind of question you can get an exact answer just by doing a bunch of paper and pencil calculations, or tablet and stylus calculations, shall we call them. The reason is because this is unfortunately not easy to calculate an exact formula for, because you're actually going to have to pounce a lot of times, and what this is actually called is it's actually called a binomial distribution. It's what happens when you're saying, I'm going to go and do some random thing a whole bunch of times, 2/3 chance of success each time, and I'm just kind of curious when my histogram of how many mice I catch goes beyond this particular 10. Right? I'm not going to be able to do this with just the stylus and the tablet because of the fact that it's not going to have a nice formula. But if what we're basically talking about here is you're saying that you are going to pounce n times 2/3 chance of success each time. And the question that was asked was, for what n is the probability of at least 10 successes? Let's put some parentheses here. Probability of at least 10 successes more than half. And that was the question. But there's no way we'll be able to actually calculate that out. Instead, what ends up happening is that, you see, if you're going to go and pounce n times with 2/3 chance of success each time, when n is big, the graph of what it looks like of how many successes you've gotten looks like a bell curve. Looks like something like this, right? If you draw something like this, what I'd say is that up here is somehow, this is what's called a probability distribution, and this is somehow the number of successes, right? And this is somehow the probability density, but this is what it looks like. And effectively, around half of this, around the middle of this thing is around 2/3 n. Because in some sense, you have about a 2/3 chance of getting successful each time. You do it n times, so you sort of expect to be right about 2/3 n of the time. And this thing ends up being a lump that's around here. But the problem is, if you want to know when is that lump going to be more than 1/2, when n is too small, you don't have what's called the law of large numbers. It's not large, right? But if you had n being very, very big, and this thing eventually became pretty symmetric, then what you would say is that somehow, maybe it would be around where this 2/3 n is about 10, right? So I'll just give you a guess right now that I'll say if n is 15, it's probably reasonable, right? Actually, I didn't expect to be able to give you that answer, but I'd say, probably for around 15, this might work. I'm a little curious. So I wonder if anyone here is on the internet and can use Wolfram Alpha. And I'm on the internet. Okay. I'm on the internet too. Let me see if I can go and figure this out. Just a second. So let me just switch around and see if I can figure this out. Just a second. Let's see. So let's see. I wonder if this thing actually works. So where are we now? So I've just pulled up this browser, so we're here. So let me see. And what I'm curious about is what happens if I try to, if I try to say I'm going to flip this coin, and I want to know if, not to flip this coin, I'm going to do something n times. I want to know what's the chance of success the chance of success is 2/3. I want to know when it's more than 1/2. So what I would do is I would say probability of binomial distribution. I wonder if this will work. Binomial distribution. And we're going to do 15 of them and 2/3 chance. Probability of binomial distribution bigger equal 1/2. I don't even know if this will actually work. No, not 1/2. Bigger equal 10. I don't know if that will work. Somehow Wolfram Alpha sometimes is able to do this. Oh, neat. It worked. I don't know if you guys can see what's going on here, but what happened is I went and said, okay, I want to know what's the probability that if I go and flip a coin 15 times with a 2/3 chance of success, then what's the chance that I get at least 10 successes? And it actually says the chance I get at least 10 successes is about 62%. So what we're seeing here is that, I don't know if you guys can see what just happened, but what we're seeing here is that somehow this is exactly the little graph, the little lump that I was talking about. And when I have this little lump I was talking about, then as you can see, I was trying to see where can that middle of that lump be at 10. And the way I was thinking about this is, as I said, well, the middle of that lump is around at 2/3 of the n. So if I use that it's around 2/3 of the n, and if that's supposed to be 10, then that means if n is 15, 2/3 of 15 would be 10. So then that would be over here, right? So then in this case, what I see is that indeed when I try it 15 times, my chance of having at least 10 successes is 61%. But now let's see what happens if I tried 14 times. Okay, so now we do it 14 times. Aha! And if I do it only 14 times, then what I find here is that I don't know if you can see this thing on the screen, but with 14 times, the chance that I get at least 10 successes is only 47.55%. So in that case, that actually shows that my answer was right. That's why I pulled out Wolfram Alpha. Because what I was saying is that somehow, you're asking, what about 14.5? Well, the reason we don't do 14.5 is because the question is asking, Bob the cat is pouncing, right? It is very hard to pounce 14.5 times. How do you pounce 14.5 times? You can't. So it's going to be either 15 or 14. And the way that I just did this thing, I'm actually surprised it worked. The way I just did this calculation is I said, well, that middle bar is going to be about 2/3 n. In order for that to be about 10, I need to have 15 for n. And so 15 was my guess for the answer. And actually it works, because 14 wouldn't work. 14, as you see from this Wolfram Alpha calculation, would give a chance of success, meaning if you jump 14 times, your chance of success is only less than half. So we actually answered the problem. Okay. All right. So I'm surprised that this thing worked. Oh, Nathaniel Potter asked, why is bell curve? Well, that's a deep point. That's actually something called the central limit theorem. There's a very interesting theorem inside statistics. There's actually a nice proof using Fourier analysis. But there's a way to show that if I kind of repeat the same thing over and over and over again, then the average of the measurements actually converges to this kind of a picture. Okay, nice. So it actually worked. More questions. Yeah. I will say I'm actually surprised that it worked, but as I was talking about this, at first I was like, oh my gosh, do I really want to write down all those chooses and add them? And I said, no, you guys must know by now. You must know by now that I'm really lazy. I will refuse to do those kinds of calculations that you have to actually, do a bunch of calculations. But on the other hand, as I started writing this out and saying it and telling you about the story of this binomial distribution, it suddenly occurred to me that, this n might not be too small after all. Right? So somehow if I, since I need this to be 10, I was like, that's n equals 15. At n equals 15, the binomial distribution already looks like a lump. A specific lump. It already looks like this bell curve. And so that's why I was kind of curious, and that's why I yanked out this Wolfram Alpha. All right, more questions. Oh, I see that somebody here was at the North-South Foundation presentation. Welcome back. I'm happy to see you, or welcome to this, I guess. Welcome to see you. Nice to see you. Okay, more questions. Here's a general question. It's not about math, but it is sort of. AC asked, tips for productivity in the summer. I think that the summer is this very long time when you don't have anything that you really have to do. And it's very easy to kind of wake up and, have breakfast and, kind of drift around. And after a while, it's time for the live stream. And then you drift around some more and then the summer is gone. Right? So that's the thing about the summer. And it's much better if you kind of say, hey, I think I want to try to do some stuff. Get some structure for yourself. Make maybe some goal. Do something, right? Do something meaning I would like to make a project. If you go and decide you want to make an art project, make a writing project, make a computer program project. If you decide you want to go and do the problems inside this particular contest that you haven't really gotten the time to play before, then you're like, all right, how do I finish this task? How many of these can I do a day? How many of these are there to do? You know what I mean? Basically, you don't have someone telling you what to do. And that's the best thing. I love being in situations where nobody's telling me exactly what to do. Then you can go and decide and decide, I decided I want to do this task. And that's my choice. And then suddenly, it'll be a great way to use your time for the summer. Christine Ju asked, did you memorize the nutrition facts for a banana? I have not, but I have noticed from experience that eating like 3 bananas can get me going for a while in the morning. So I've noticed that. Although I have a feeling that's probably not enough calories. So that's only enough to last you for a bit until lunch. I understand that bananas are also pretty good for you with potassium too, right? So maybe my suggestion is like with the banana, another thing about bananas, it depends how large the bananas are. There are different sizes of bananas, as you know. Some of them are medium, some of them are large, some of them are tiny. And actually, fun fact about bananas. I don't know if you guys know this, but I only learned this, only a few years ago. But actually, all the bananas on Earth are basically clones of the same kind of banana. So there's like basically only one kind of banana that most people buy in the United States of America. And there might be medium size, small size, giant size, expert size, but the bananas are actually, there's like only one kind. What's that kind called? Does anyone here remember? Is it called like the Cavendish or something? I already forgot what they're called. But there's like one kind of banana that's being grown. And I think it starts with a C. It's like a certain kind. And that's also why, as you go around and buy bananas in different parts of the country in the US, they're like all the same. If you think about it, it's pretty remarkable that they're all the same. But Cambrian banana? I'm not sure it's the Cambrian banana. That doesn't sound quite right. Cavendish. I thought it was the Cavendish banana. And you're saying it's called banana. But the fun fact about bananas is that actually it didn't used to be that this was the main banana. There was actually before this a different kind of banana that was what everyone was buying all around the world. The other kind of banana, I believe it was called the Gros Michel banana. Grosmichel. I'm not sure if I'm 100% right. I'm making stuff up. Well, maybe not making stuff up. I'm trying to go from memory, okay? And any of you who are on the internet are probably able to fact check this thing and help it be more accurate. But I believe it's called the Gros Michel banana. And the deal is it used to be that everyone only got that banana because that was actually a better banana. But then what happened is that, like all of the bananas in the world, almost all were that kind of banana, Gros Michel. And then there was a banana disease. And that banana disease wiped out that kind of banana. Because that's the danger if you happen to have like only one kind of crop. If you have only one species of banana, then unfortunately that got wiped out. And then somehow everyone went to find out what's the other one that I can use. And we all switched to this Cavendish, which was like the second best. Now I see all these people in the chat saying, what do you mean there's only one kind of banana? There's tons of bananas. Actually, that's true. If you go to other parts of the world, or if from my studio here I walk down the street to a Mexican supermarket, you suddenly find out there's like a bazillion types of bananas. And some of them are really small and narrow. Some of them are really big and like they're short and they're squat. There's like all these different kinds of bananas. And so, it's actually not true that there's only one kind of banana, but you're only used to seeing these. And there's all these other kinds. And if you're curious, why don't we see all the other kinds around? I believe that the thinking was that this particular kind of banana that we sell is the one that transports the easiest. because otherwise, if the banana turns black and spotty, it doesn't sell as well. All right, enough about bananas. Let's go on and do something else. I see. You guys are saying I'm a bananologist. I mean, it's partly because I do feel that bananas are pretty efficient ways to get nutrition and energy. All right. Oh, David Tiang, you're asking, have you met Titu Andrescu? Yes, he was my coach. I mean, when I was doing all of these math contests, he was the first math Olympiad coach that I really had. I mean, the first head math Olympiad coach that I ever saw. In fact, when I went to the contest a long time ago, he was the team leader of the United States of America. So, yeah, Titu Andrescu, very, very good guy, taught me many things, and I appreciate him very much. Okay, more questions. Sammy Cisneros H. Where can I find info about theorems that could be useful? Yes, this is a good question, because if you saw what happened in today's live stream, at some point there was a problem about number theory, and then somehow I just pulled out of my hat this Fermat's little theorem. So you're probably wondering, where is the big list of all the theorems that I need to know in order to do all these problems? My advice to you would be, it's not really that there's a theorem list, as much as there's like getting a level of comfort in the problems. And as you get a level of comfort in the problems, then after a while, you just somehow understand that some facts or patterns just happen to be true. And after a while, those settle in as theorems as well. I actually don't recommend trying to find a big list of theorems and memorizing them, because if you just see a lot of theorems and memorize them, you'll never quite know when to use it. On the other hand, what you just saw me do was like, here was a problem that came in from the crowd, and I don't even know what they pulled on me, but something came in. And then we just started using wits. We started looking for patterns, we started trying to express things, and after a while we realized, oh boy, it would be useful, so useful, if I could say that somehow the powers of 10 eventually repeated when I looked at remainders. And that's what motivated that theorem, the Fermat's little theorem. So the point is, if you are a lazy minion, I guess that's what they're saying about me. But I'm not wearing the banana shirt today, so I don't quite look that way. But somehow, if you're trying to learn all of these different theorems, my advice is to go and do problems that are at around your difficulty level, at around your experience level. And after a while, you'll actually start to discover that I keep running into this kind of a technique. And then that technique will stick on you. Okay, more questions. Oh, let's do this math question. This is a relatively quick one. Oh, yes. Somehow I put my pen in the computer. So there was a question about the difference between convex and strictly convex. A convex function can look like this. So that's a convex function. And convex just means that somehow if I looked at the shape, convex function, oh, actually you probably didn't even say function. You just said convex and strictly convex, so I can just even say convex shape. That's a convex shape, which is something which looks sort of like a banana. And convex just means that if I looked at all of the stuff that way, then if I ever were to try to connect two of those points in the stuff by a line, the line stays inside. But sometimes that line could be like right along the edge. This is okay. But if I want something that's strictly convex, strictly is strict. I actually am not allowed to have part of the edge be a straight line. So in fact, for strictly convex, I would need to have something that looks like this. And let's pretend that there's no like actual flat spot on here. So I'd say that's maybe the answer to convex versus strictly convex. Okay. I'm trying to see what's a good question to go and finish off everything today with. All right, I'll finish off with a comment that I saw someone here say. It is 5 p.m. and math is cool. So I hope that what you saw here today is that we saw a bunch of different ways that we found patterns in math. And when you say math is cool, I actually also agree. I always think it's neat when you can kind of use some mathematical understanding to prove something that's pretty hard or to solve something that's pretty hard. And it looks like for some reason my stream just ended. Just a second. Hopefully we'll be back soon. We got a lag. huge lag. It looks like we just had a stream drop. Oh, it's back. Hi. You're back? Okay, so I'm not entirely sure if it's all back for everyone, but I can see that on our indicator has shown that the whole system is back now. So I'm looking at this. Yes, okay, I think we're all back now. We're all back now. Great. So maybe let me just sum up, right? So math is cool. It's cool to be able to see these kinds of coincidences. It's cool to be able to see that sometimes you can use some understanding somewhere to understand a question which is somewhere else. And so that's neat. And you can use this for more powerful things too. With that, I think that since we did hit 5 p.m. and the lag was also trying to tell us a message, which is that I think we're done, in that case, we're done. And I'll see you all tomorrow. Same place, same time, 4 o'clock p.m. Eastern Time. Take care, everyone.